So let's do sets. All right. Now, the first thing that you will need to ask yourself is, what's the definition of sets? All right. So by definition, sets are this, okay, is the collection, okay, of well-defined objects, okay, or distinct objects. So in other words, if you're looking at sets, your sets have to be defined, or they have to be, sometimes they'll use the word distinct, okay, distinct, okay, in a way that's different, all right. So but I mean more interested in the word defined. This is a collection of well-defined objects. In other words, your set has to be well defined, okay. So knowing this definition, there's something that I would like you to help you with, so that you can define your sets better. All right, this will be okay. So in other words, what I'm trying to say is, sometimes they'll tell you to maybe describe a set, right? So for you to describe a set, when they're dealing with maybe say numbers, you have to know what numbers you're dealing with, because they have to be defined. By defined, we mean it has to be very well known. It has to be known what you're describing. So a set is a collection of well-defined objects. They have to be defined. You have to describe them. All right, you have to describe them. Okay, so from this point, I'll teach you set build notation, and also we're going to define now other things that you need to know under sets. All right, so if we go to set build notation, let's go to set build notation. It's something that you learned even in grade, I think 12, set build notation. So notice how we're moving. We move from sets. We said sets, this is a collection of well-defined objects, right? So your objects have to be very much well-defined, okay? Then from there, we have to go now to set build notation, okay? Set build notation, we'll also talk about set build notation, because these things are so related. So just stay a bit along there. Definition of a set, well-defined. For example, you remember how sets were defined. If we have sometimes 1, 2, 3, 4, right? You say this is a set of numbers, right? Now the question is, what sort of numbers are you dealing with? That's a definition we're talking about. Are you dealing with prime numbers? Are you dealing with real numbers? You have to describe it. Yeah, it has to be well defined and properly oriented. Okay, so knowing that fact, let's describe first set build notation and also see how they're related to the definition of sets. Okay, so what is set build notation? So set build notation, this is a notation for specifying a set by a property that characterizes its members. Okay, in other words, let me write what I've said, then I'll talk about it. This is a notation, okay, for specifying a set by a property that characterizes its members. In other words, what we mean in simpler terms, set build notation is that you're just trying to describe what you have in a set. That's set build notation. Okay, so now what is the standard form for set build notation? So say we have a is equal to, a function of so I'll give an example, 1, 2, and 3, and 4, right? How are you going to represent this in set build notation? So by definition of set, this is a notation for specifying. So we have to specify what is in here, okay, by a property that characterizes its members. So we have to know, in other words, you have to know what is inside there in simpler terms. You have to learn how to describe it in a more mathematical way. That's what they just mean in simpler terms. Okay, so how are you going to write this in build notation? So first you have to describe what sort of numbers do you have inside here. I'll define for you what numbers are there. Okay, so how are you going to write this in set bit notation? So you're going to say A is equal to, okay, so you're going to introduce a property that characterizes these members, this, for specifying, okay, a set by a property that characterizes its members. So I'm going to introduce a property. So what property am I going to introduce? I'm going to say X. Okay, I'm going to say whatever is inside is X, but such that this is a stroke there, such that X is a member of, then I'll describe whatever is in there. So for example, these are numbers 1, 2, 3, 4. I'll write that. So let's say, for instance, A is equal to a set of, give an example, Toyota, okay, Benz, okay, Mark X, okay, what else? Whatever car, Mazda, right? Mazda. How are you going to write this in set B notation? So I'm going to say A is equal to, so I'm going to introduce that a property, so that property will be X. So whatever is inside here will be X, but such that X is a member of. Now you have to describe. What do you have here? No wonder I had to write for you this. You have to describe it, isn't it? So it's equal to X such that X is a member of. You have to describe this now. What is this? Brands, right? Brands for what? For cars. Isn't it? This is a brand for cars. You have described it in set B notation. So you have answered X such that X is a member of what? Brands for cars, right? Or it's a member of cars of different brands. So you have described it by introducing what? A property. And what is that property? X. So knowing this fact, mostly the questions that will be there will be maybe for, give an example, maybe say number. Let's first define numbers. Definition of numbers, right? Definition of numbers, okay? Definition of numbers. What numbers can you have there? Okay, so number one, let's start with whole numbers. Whole numbers. Okay, so what are whole numbers? Okay, these are numbers. These are counting numbers. Counting numbers. Okay, starting from 0 to positive infinity. So we're talking of numbers like 0, 1, 2, 3, 4, 5, 6 until infinity. So these are counting numbers. If you're counting, you start from 0, isn't it? So 0, starting from 0. Okay, starting from 0 to positive infinity. Okay, then number 2, we go to real numbers. We go to natural numbers. Natural numbers. What are natural numbers? Okay, you can say these are counting numbers. Counting numbers. Okay, starting from where? Starting from 1. Starting from 1. Okay, so these are natural numbers starting from 1. All right, so these starting from 1 to positive infinity. So for example, looking at 1, 2, 3, 4, 5, 6 ... to positive infinity. Okay, then usually this is denoted by, natural numbers are denoted by sort of N. Okay, then this is not denoted by W, stuff like that. Then after this, we can go to natural numbers. We can go to odd numbers. Okay, what are odd numbers? In case you don't know, in school, this is very important. I know I've taken you back to grade like 8, but this is very important. What are odd numbers? So these are numbers. All right, these are numbers. All right, these are numbers that are, okay, these are numbers that cannot, okay, be divided evenly. Okay, evenly by 2, right? In other words, they always leave they always leave a remainder, isn't it? They always leave a remainder. Always leave a remainder of 1 when divided by 2. By 2. Okay, what numbers are we looking at here? So we're looking at numbers like 1 2 1 3 5 7 9 11 13 15 17. If you can see the pattern, right? So they can't be evenly divided by 2. Okay, then we go to prime numbers. Okay, prime numbers. Prime numbers. What are prime numbers? Okay, prime numbers. What are prime numbers? So prime numbers, we're looking at numbers that are divided by 1 and itself, right? 1 and itself. So these are numbers that can only be divided by 1 and itself. You can write that. So numbers that can only be divided by 1 itself. Can only be divided by 1 in itself. So excluding 1, okay? Excluding 1. 1 is not the prime number. So we're looking at numbers like 2, 3, 5, 7, not 9. 3 can be divided into 2, 9, isn't it? So looking at 11, 13, 17, 19, 23, 29. So these, etc., etc., isn't it? Okay, so on and so forth. So let's go to the fifth one. We're going to go to apart from prime numbers, let's go to integers or to real numbers. Okay, real numbers. What are real numbers? Okay, so real numbers, these are numbers okay, from negative infinity to positive infinity. Okay, so real numbers, and they're denoted by R. Okay, so real numbers are numbers from positive infinity to negative, from negative infinity to positive infinity. What of integers? Okay, integers. Now guys, notice these real numbers include fractions, decimals, and everything else. In other words, this includes fractions, okay, decimals, stuff like that. Then integers, when we look at integers, we're going to say these are numbers, okay, numbers from negative infinity as well to positive infinity, but we're going to excluding, okay, fractions and decimals. Okay, then we'll go to the seventh one. So integers, I'll give an example. Is integers, we're looking at numbers from negative infinity to positive infinity. We're looking at -2. Okay, number line. Numbers on a number line. On a number line, we don't have -0.2, right? If you come to varsity, -0.2, stuff like that. This is not an integer. Okay, integers, we're looking at -2, 1, 4, 6, 8, 9. You know what I'm saying? So, but what if you have 3/4? This is not an integer. 2.1, not an integer. -3.1, not an integer. Integers should exclude fractions and decimals. Then number 7, what are we going to look at? We can look at rational numbers. Okay, rational numbers. What are rational numbers? These are numbers in the form, I'll talk of this is a topic by itself. Rational numbers, these are numbers in the form of a over b. Okay, like 4/5, 6/7, 5/2, numbers in that form. What of irrational numbers? Irrational numbers. Now notice rational, it's in the form of that. Irrational numbers, these are numbers that are not in the form, that are not in the form a over b. In other words, numbers that cannot be expressed as a fraction. For example, we're looking at the square root of 2, square root of 3, 1 minus the square root of 2, square root of 3 minus the square root of 6. These are irrational numbers. They can't be expressed in the form, they can't be expressed as a fraction. Okay, then number 8, then number 9. Okay, number 9, we can look at complex numbers. What are complex numbers? So these are all topic by themselves. Complex numbers, these are numbers in the form a plus bi. I'll talk about this. A plus bi. For example, 2 plus 3i. Now this I part, a and b are members of real numbers. Okay, and I means imaginary. In other words, it doesn't exist. Something that is imaginary, isn't it? Imaginary. Okay, so for example, 3i, 2i, 6 minus square root of 3i. The fact is, there's this I, it makes it imaginary. Or if I want 6 minus 10i, or 7 plus 14i, these are complex numbers. Okay, so these are numbers that you really need to know, guys. The definition of these numbers you really need to know before you come to varsity. So let's do another video now to continue on to do examples on set build notation. Yeah.